Hey everyone, so we're going to continue our discussion about horizontal projectiles. And now we talked about the setup. Now we're actually going to talk and do some practice problems. So let's start off with this first one. Remember, you're going to fill out that XY chart. So pause the video, work yourself, and we'll go over in a second. All right, so for this one, like I said, we want to set up a chart. Again, as we fill it out, we want to constantly ask ourselves, what information do I know, and is it X or Y? So for example, this initial velocity is going to end up going in the X direction because it's being shot horizontally, and this height is going to go in the vertical direction. So my chart should end up looking like this. Initially in the X, I'm starting at 0, and with some initial height of 1.5. I'm going to land some distance away from the cliff. I'm going to land on the ground, so that's Y is going to be 0. My initial and final velocity in the X are 200 because my acceleration is 0 and it's constant speed. And then in the Y direction, my initial velocity is 0 because it's shot only horizontally. There's no vertical aspect, and the acceleration is pulling it down at a rate of -10. So looking at this, they want to know how long does it take for the arrow to hit the ground. Now, when you set up the problem, if you have more than one piece of information missing in the X direction, you pretty much can't use it. So if you're missing either position, velocity, or time because the acceleration is 0, we won't be able to use the X direction. You can check this out yourself, but what you'll end up getting is with the acceleration, you'll get, if you use the timeless equation, you'll just get v squared equals v naught squared. If you use the acceleration equation, you get v equals v naught. And if you try to use magic d, you'll just get up with d equals v naught t. So you need two of those three variables, d, v, or t. So from here, we're going to use the y direction. And this is actually super common. Based off of what we're going to use, we're going to find, we're going to use the annoying x equation. Notice that I did switch out the x's for y's, just because it's a vertical thing. Plugging in the information. Now, again, we split it up into x and y for a very specific reason. So we're only going to be using the y side here. So I put in only the y information, and I end up getting that the time is 0.548 seconds. All right. Now I can put this into my chart afterwards, and then the next question says how far does the arrow land? So that's a horizontal distance. Even though they don't explicitly say horizontal, I can figure that out based off of the wording. So I want to find the horizontal final position. Again, based off of the information I have, the only one that works out is the annoying x equation. This is actually one of the reasons why I call this the annoying x, because not only is it the longest equation, and the way that you see it on the reference table, there's tons of x's, but it's annoying because it's useful so much. We do it, and it's like our go-to equation for a lot of these questions, especially projectiles. So that makes it even more annoying. And it also has that quadratic aspect. So we're taking the numbers only in the x direction, making sure to carry over that time from before. And I end up getting that it lands 109.6 meters away from where it was initially shot. All right. Here's the next question. Pause the video by yourself and we'll go over in a second. All right. So once again, based off of the information, I need to fill out my chart. Now, just like before, they give us this initial velocity, which is only going in the x direction. They do tell us the time this time around, so that's pretty nice. I can put it in both x and y. The one thing that I want to be careful of is this. They tell me 100 meters. Now, if I'm not reading carefully, I might put this into the chart, but I don't actually use that 100 meters because the 100 meters is representing a physical description of the scenario. It's saying that the rocks only go up to 100 meters. So this is what we call a reference number. They want to know, does Crazy Jeff clear it, or does he end up hitting into the rocks? So the real question is, where does Jeff land, and is that position greater less than or equal to 100. So I'm using the answer to compare to this. So when I make my chart, it's going to look like this. This is all the information that I'm given. From here, I can actually see that since I have only one piece of information missing in the x direction, I had everything else. I could just use the annoying x equation, plug the numbers in, and get an answer of 200 meters. Again, the 100 meters is a reference point, so 200 is greater than 100, so he's clearing the 100 strip, which means that he doesn't have to retake physics. Turns out his math is really good. So this is basically what we found. These rocks go out for 100 meters. So we want to know, is this number, the final position horizontally, greater than 100? And we found that yes, it is. It's 200. All right. Here's the next one. Pause the video works off. I'm going to go over in a second. Now, they want to know which one hits the ground first. So you can do math. But there's a few other ways to do this. First, I actually did mention I kind of hinted at what the answer was in the previous topic. I'll reiterate that later. But what I can do is I can actually write down the given information. The good thing is you'll see that I don't actually have to continue from there. So if I start with the free fall, this is the information I have. If I follow the information, initially it's starting at some height, it's going to land on the ground, so that's 0. It's being dropped, so initial velocity 0, and acceleration is pulling it down at -10. When I do the same thing for the horizontally shot arrow, my chart looks like this. Same numbers for the y. In the horizontal, we're going to say that this is 0, that the 20 meters per second is horizontal, and the acceleration 0. Now notice the y values are the same. And one of the things I kind of mentioned in the previous problem is that these y values will actually end up being used most of the time to find time. Because it turns out that it's the vertical aspect, the initial velocity in the y direction, the initial position in the y direction, the acceleration in the y direction. These values are what affects how long the arrow's in the air. If I change a number in the x direction, that doesn't necessarily change my time. It's only a change in the y values that affect time. So if these numbers are the same, I know that they're going to land at the same time. This initial velocity in the x direction only affects where it lands. So both of these will actually land together, but A is going to land further away because of its initial velocity. Mythbusters does a really nice video where they actually test this with a bullet dropped and a bullet shot, they do find that for the most part it is the time difference is very negligible, and it could be attributed to a bunch of different things such as air friction, time delays, things like that. But it's fractions of a fraction of a second difference. Ideally, the two things should end up landing together, just at different locations. Now, I did mention before that I said this in the previous video that I hinted at it. I mentioned that the arrow shot in the horizontal projectile will end up hitting the same vertical positions in the same time. So the amount of time this takes to fall a certain distance, this arrow has also fallen horizontally a certain distance. And then if it takes 3 seconds to fall to its new distance, 3 seconds later, A is going to fall vertically the same distance. So if we extrapolate that, the time it takes for this to fall down should equal the time it takes this to fall down, because vertically they should be at the exact same level every second in their motion. So this is a super common question that gets asked a lot, and it's important to just kind of remember and reiterate that these two objects will always land together. They just land at different locations. Now, one thing that you're going to need to know about horizontal projectiles, and actually projectiles in general, are the factors that affect it. Like what affects how far it lands, what affects the time in the air. We kind of already talked about this. So a good question would be, Does mass affect range or time in the air? Well, the answer is no. As I said, in the ideal case, this doesn't affect it. Um, if we're talking about air friction, on the other hand, mass would affect it. The greater the mass, let's see, the greater the mass, the closer the range will be to its ideal time, and the lower the time. Um, yeah, and this is only true for with air friction, and that's mainly because of the fact that bigger masses are going to be less affected by air friction. So they're not going to they're going to go pretty much closer to their ideal path and fall in the air a lot quicker than because they're accelerating more than objects of lighter masses like feathers. But again, for the most part, if we're talking about an ideal case, which is going to be 90% of the time, mass has no effect on it. None of the equations deal with mass. Another question you could ask is, what does height affect? Does height affect the range? Does it affect time in the air? Does it affect both? And how does it affect it? For this one, the answer is yes. And the answer is yes to both. If we increase our height, the initial position in the y direction, so I'm going to write it like this. Actually, let me erase that. Uh, my initial y position, if I make that higher, well, that means that the object's going to be in the air longer. And since it's going to be in the air longer, that means that the final position in the x direction will also be further away. Because remember, the time in the air, the object's moving horizontally at a constant speed. So the time in the air is going to mean that it's going to move at that constant speed for a longer amount of time. So instead of landing on the ground 5 seconds later, it landing 7 seconds later means that it's going to travel 2 extra seconds longer horizontally. So height actually does have an effect on everything. Another question is horizontal velocity. Does that affect range, and does that affect time in the air? And how does it do it? And the answer is yes/no. So one thing that we did mention is that the initial horizontal velocity, if I increase this, then that does actually increase the range. Because as we talked about, if it's going to take 5 seconds to land, if it was traveling at 1 meters per second, that means that it only gets to travel 5 meters horizontally. But if I now increase that to 100 meters per second, that 5 seconds it's in the air means that it can travel 5 meters longer. So it ends up traveling a lot further if that initial velocity in the horizontal direction is higher. But as I mentioned before, that does not affect time in the air. So my answer to the time in the air is no. Horizontal information really only affects horizontal information. Time isn't really affected by the horizontal. Now, I could also ask what other factors could affect range or time in the air. And there's a bunch of things that we could go to. If we were going to open this up so it wasn't just horizontal projectiles, we can mention angles. We'll talk about this later, but angles also will affect time in the air and range. For the most part, increasing this will end up, well, it'll have a weird effect on the range. The range could go up, it could go down depending on what angle it is, but the time in the air will always end up increasing. Gravity, how does gravity affect it? Well, if I increase gravity, then both the range will decrease and the time in the air will decrease, because now it's going to accelerate much quicker downwards. It's going to land quicker downwards. So these two numbers will end up being a lot smaller. Anything dealing with air friction. I'm going to call this air friction. If I increase this air friction, well, that's kind of just decreasing the general acceleration. So that kind of flips everything. So this is going to decrease the range, and this one will actually uh, increase the time it's in the air a bit, depending on the setup. Um, I think that's about it. There are other factors, um, that we could talk about, but I think those would be the main ones. All right. Another thing to mention is there's a good chance that you might be asked what the final velocity is for an object that's acting parabolic. So, one thing to note is when it's moving in that parabola form, we have two velocities now. So we're going to end up having a horizontal aspect of the velocity and a vertical aspect, depending on where we're located. Initially, we don't have to worry about that because it's all horizontal. It's none of it's vertical. But as we get further and further along, this vertical aspect increases. So what we're going to end up having to do is use Pythagorean theorem to figure out what the actual velocity is. Now note, this only gets used if and only if they ask for the total velocity, the resultant velocity. If they mention that, well, like total or resultant or some sort of thing hinting at that, and they don't explicitly mention a component of the velocity, then that's what you're going to end up doing. Pythagorean theorem, and then they might ask you to do SOHCAHTOA for direction. Typically, the angle will be taken from the horizontal. So, you make your little chart, your little right triangle diagram. You could use a tangent, do, um, according to this, tan theta is opposite, which would be the y component, divided by the x component, and then you could use that. Like I said, it's not super common that it gets asked. It gets asked every now and then, so definitely keep an eye out for it. So this is kind of how it gets asked. Like I said, it could ask just straight up what's the velocity, or it could ask for total velocity, resultant velocity. Basically, again, the idea is that they're not mentioning components. They're not mentioning a certain direction. They don't say the velocity in the y direction. They don't say velocity in the x. They just kind of leave it as a velocity. So that's when you'd have to do this. All right, here's the next one. Pause video where itself. I'll go over in a second. So one of the things I mentioned when we talked about air friction in the last unit with vertical projectiles, I mentioned that you really only have to do conceptual questions. This is a perfect example of a conceptual question where you'd have to use or understand air friction. So here they give us this sketch of the ideal path without air friction, and they want to know, well, what would it look like if there was air friction? If air friction wasn't negligible. Basically, the thing to remember is that what ends up happening is the object is going to start decelerating horizontally now. There's going to be air friction pushing it this way, meaning it's going to be slowing down as it moves. So it's not going to go nearly as far. Also, it's going to be decelerating vertically as well. So it's going to take a while for it to actually land. So its path is going to look like this. Initially, it'll start following the path, but then it's going to fall and taper off. It is important that you actually do make sure that you sketch it starting initially in that ideal path. If you just did this, that doesn't work because again, we have to start at the same initial path, but then start deviating as time goes on. Because again, air friction is something that affects the object gradually over time. The longer it's in the air, the faster it's going, it's going to be affected by air friction more and more. All right, this should be the last question. So pause the video, work itself. We'll go over in a second. All right, so this is actually a pretty good example of how you might start seeing questions in the AP. Now, so far, the questions, because we're only doing kinematic stuff, the questions should maintain this realm, this concept of talking about motion. But once we start getting into the aspect of forces, and especially once we get to energy, you're going to start to notice that we're going to be getting questions with a lot of things that mix around where we can actually combine different aspects together. We can have a problem that combines energy going into forces, going into projectiles. It's important that when you do those problems that you isolate each of the aspects. You isolate the each unique motion. You isolate the energy section. You isolate the forces, and you isolate the projectiles. This is something that you'll get practice with, so don't worry about it too much. But this is a good example because this question was one where it combined energy, forces, and projectiles all together. But you didn't need to know that for this aspect. So the question is, what would the path of the person do if he let go at these locations B, C, and D? Well, at B, the velocity, so this represents its trajectory. It turns out we didn't really mention it too much. I kind of showed it in the diagram before, but the velocity always acts tangent to the path. So in part B, it's going to act horizontally. Part C, it's going to act somewhat on an upward angle. And then D, because this is its maximum height, its velocity is going to be 0. So there's actually no velocity at D. So if I take this and relate it to my projectile stuff, well, since B is going to end up moving horizontally, that means that it's going to look like a horizontal projectile. Easy enough. It's going to start going flat and then fall down. C, C is going to have this little, it's going to be shot at an angle. Now, we haven't talked about angular projectiles, but I'm pretty sure you could probably guess what it might look like. It's going to look like it starts going up and then it's going to come back down. Again, it's a parabola. It's a parabola just going to a maximum height. D, on the other hand, because again it's at its max height, there's no velocity, there's nothing forcing it to move horizontally, therefore it's just going to fall straight down. So these are the three different motions at these locations. Again, this is a very nice free response that you might see where, again, you combine different aspects together. So it's important to note how projectiles get set up and kind of recall when you can do it. In fact, you want to try to constantly think about, is this a projectile? What type of projectile is this? And figure out how to kind of set up the problems that way. All right. That's pretty much it. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.